In this section, we talk about classification and the model logistic regression that deals with classification. We're going to talk about what is classification, why not using linear regression to do classification. We're going to talk about binary classification with binary response variable and the logistic regression model, how we estimate the simple logistic model, and then we're going to move doing classification using the logistic model. We have seen before data like the advertising data. We have, in particular, three predictors: the TV, radio, and newspaper budget, and a response variable, which is continuous or quantitative. There are data, though, that the response variable is not quantitative. For example, the hard data. And the hard data contains a binary or qualitative outcome, which we call AHD, for 303 patients who presented with chest pain. The outcome value here is yes, which indicates the presence of a heart disease based on angiographic tests, or no, which means no heart disease. The data also contains 13 predictors, including age, sex, 0 for women and 1 for men, the cholesterol measurement, the maximum heart rate, and the rest blood pressure. Linear regression performs well on tasks that require the prediction of a quantitative response variable. For example, the number of taxi pickups, the number of bike rentals. When the response variable is categorical, regression techniques are no longer applicable. Such tasks fall under the umbrella of a classification problem. For example, whether the next taxi is going to be yellow or blue or black. And the goal of classification problem is to attempt to classify an observation into a category, also known as a class or a cluster, which we label by Y, based on a set of predictor variables, which we label again as X. Classification problems are ubiquitous in many domains, such as healthcare, finance, or sports. Some examples of classification problems are to determine whether a startup is worth investing in, to determine the disease type of a patient based on various genomic markers, to determine if a certain candidate athlete is suitable for a particular sports team, or to determine if a given image is real or fake. Why not linear regression? Let's talk about a concrete example. Given a data set, x1, y1, all the way to xn, yn, where here y's are categorical, the aim, again, is to predict which category y takes on a given value of x. A categorical variable y can be used as is, because the computers cannot take as an input a category, red, blue, yellow, but it could be encoded to be quantitative. For example, if y represents the concentrations of Harvard undergrads, then y could take the value 1 if it's a computer science, 2 if it's statistics, and 3 otherwise. A linear regression could be used to predict y from x. This model will imply, though, a specific ordering of the outcome and will treat one change in y equivalently. For example, a change from y is equal to 1 to y is equal to 2, from computer science to statistics, is considered the same as change from y is equal to 2 to y is equal to 3, from statistics to everyone else. However, this change should not be interpreted as the same. Additionally, if the ordering of the response variable is changed, the model estimates and prediction would be fundamentally different. For example, a model trained with y is equal to 1 to represent statistics and y is equal to 2 to represent computer science is different from a model trained with the original ordering. Now, if a categorical response variable is ordinal, has a natural ordering like freshman, sophomore, junior, etc., then a linear regression model will make some sense, but still not ideal. The simple form of a classification is when the response variable y has only two categories. There is a natural ordering of the categories. And for example, if we want to predict where an undergrad student lives, and y is equal to 1 if the student lives in the quad, and y is equal to 0 otherwise, a linear regression could be used to predict the probability of y is equal to 1, the probability of a student living in the quad, directly from the predictors such as sex, age, GPA, etc. Now, if the probability of y is equal to 1 is greater or equal to 0.5, we could predict that the student lives in the quad and predict other houses if probability of y is equal to 1 is less than 0.5. Now, what could go wrong with the linear regression model? Let's look at the example of the hard data. And here we only consider the maximum hard day. The blue dots represent patients. There's 0 if there's no heart disease, and 1 if there is heart disease. And the orange line represents the linear regression prediction for the probability of having a heart disease or not. Now, what we can do? Since we know linear regression yields values for probability that are larger than 1 or smaller than 0, what can we do to fix it? Well, we can transform the output of linear regression to something that is bounded between 0 and 1. So which is that function? Well, logistic regression addresses the problem of estimating the probability p y is equal to 1 to be outside the range of 0 to 1. In particular, the logistic regression model uses a function called a logistic function to model p y is equal to 1. And that logistic function has the following form: is exponential beta 0 plus beta 1x divided by 1 plus the exponential beta 0 plus beta 1x. Using the logistic function will result in a model that will predict probability of y is equal to 1 with an S-shaped curve, which is in the general shape of the logistic function. How does it look, and how do we control it? Where the logistic function goes below 0.5 or above 0.5, where the probability of y is equal to 1 is above 0.5 or below 0.5, is controlled by the negative of the ratio of beta 0 and beta 1. We can examine that by changing beta 0 and see how the shape change of the logistic function. As the beta 0 decreases, the switch between 0 and 1 will move from left to right. And how fast it goes from probability is equal to 0 to the probability is equal to 1, the slope of the S-shape, is controlled by beta 1 over 4. We can also examine how the shape of the function changes as we change beta 1. As the beta 1 decreases, the slope decreases as well. And we can see for negative beta 1s, it goes from high to low as x increases. And when beta 1 is positive, it goes from low to high as x increases. How we interpreted the beta coefficients? With a little bit of algebraic work, the logistic model can be rewritten as the log of the odds to be equal to the beta 0 plus beta 1x. Odds here is the ratio of probability of y is equal to 1 divided by the probability of y is equal to 0, which we can write as 1 minus the probability of y is equal to 1. How can we use logistic regression model to perform classification? That is, how can we predict when y is equal to 1 versus when y is equal to 0? We can classify all observations for which the probability of y is equal to 1 is greater or equal to 0.5 to be in the group associated with the label y is equal to 1. And we can classify all observations of probability of y is equal to 1 to be less than 0.5 to be in the group associated with y is equal to 1.